is Dr. Vijaykumar Varma. I am presenting my results on novel magnetofluidic system to cool a solar cell. I am from School of Material Science and Engineering, Nanyang Technological University, Singapore. Heat transfer by natural convection is slow. We can make it faster by using a magnetic fluid. So under an applied magnetic field, this magnetic fluid exhibits thermomagnetic effect. So thermomagnetic effect is a temperature dependent phenomena where cold fluid is strongly attracted towards the magnet and hot fluid is not attracted towards the magnet. So what happens when this gradient magnetization is present, this cold fluid which is attracting towards the magnet replaces the hot fluid which is present here at the bottom of this container. And in doing so, it replaces the hot fluid. And this cycle repeats. We can utilize this effect by rotating, rearranging, and making the system closed loop, which results in magnetofluidic cooling system. Main components are, of course, magnet, a heat load which we want to cool, and a heat sink where heat is required to be transferred. So what happens when magnet is present? This cold fluid get attracted towards the magnet, and as soon as it reaches close to the magnet, and due to the presence of the heat load, its temperature increases and it loses its magnetic response. So no longer attracted. But due to this initial motion, it pushes the hot fluid which is already present here, and this hot fluid moves towards the heat sink. And as the system is closed loop, this process gets repeated. So what we are doing, we are cooling the heat load by using the energy of the heat load by itself. So gradient in temperature and gradient in magnetic field are required to achieve that. So why it is important? Because there is need and market for cooling devices. We are targeting to disrupt the cooling market of $368 billion by using our technology. There is need in every temperature range for cooling devices. However, conventional cooling technology is limited by noise, energy inefficiency, maintenance, ozone layer damage, and needs for rare earth elements, and it is slow and costly. And in comparison to this, our technology offers high energy efficiency. It is noise and vibration free. It is green technology. It is low cost and faster compared to conventional passive cooling technologies. Hence, it will be very interesting to see how and in what scenarios we can use our technologies. So our main target applications are in compressor industry, automobile and battery cooling, and of course electronic cooling. So in addition to that, there is also need of solar cell cooling. Why? Because for solar cell, the performance of solar cell decreases with increasing temperature. And presently, there are four main technologies which are utilized. One is floating, tracking, concentrating cooling. Other is forced water circulation, water spraying, and phase change material. So all these technologies uh, not energy efficient, and they are costly, and that's why we need new technologies which is energy efficient, environmentally friendly, and it is faster passive technology. So earlier we developed a thermomagnetofluidic analysis setup to know dominating factors for the magnetofluidic cooling device. And we observe change in flow behavior uh, with increasing heat flux values and role of vorticity as a function of heat flux values. And we develop a simulation-driven system design in our earlier publication, and we found that viscosity and magnetic properties are the main dominating factors for the device. If we if we utilize these two factors efficiently, then we can improve the device performance. To determine the role of those dominating factors and enhance the device performance, we developed 8 types of the ferrofluid. F0 is the ferrofluid which we used in our previous publication. And ferrofluids from F1 to F7 are the ferrofluids with decreasing viscosity values. Ferrofluid sets F5 to F7 uh, are with decreasing magnetic properties. We used all these sets to perform detailed investigations, and those detailed investigations were performed by using this setup. So our setup consisted of our MFC device, a data acquisition system, and a heat load power controller. And by using those 8 sets, we finally determined effect of different magnetic and hydrodynamic properties used for investigation. Our investigation for each set of the ferrofluid consisted of 12 heat load profiles. Each heat load profile consists of a heat flux value ranging from zero point 0.5 to 10, and each heat flux cycle consisted of one on-state profile and the profile obtained after turning off the heat load. And for that heat flux range, temperature increases from 45 to 300 degrees C. And evidently, each heat flux cycle is of 80 minutes. Effect of hydrodynamic properties was determined by by investigating effect of viscosity. So viscosity decreases from F0 to F5. F5 is exhibiting viscosity value around 5 cp. So to know whether the given profile exhibits superior performance or not, we should compare it with the profile of the fluid F0, which is having higher magnetic properties, around 22 millitesla, and the fluid F1 to F5 are having magnetic properties of 11 millitesla. So if a profile is above this black profile, then it is exhibiting lower performance, and if it is below this profile, it is exhibiting superior performance or higher cooling of the heat load. That is what we want. So evidently, lower viscosity value profiles exhibit continuously exhibit superior performance for all heat flux values, and uh, the profile of F4 exhibit nearly the best performance compared at all heat flux values. So, and the profile for at higher viscosity corresponding to F1 and F2 exhibit lower performance compared to our standard ferrofluid. Hence, decreasing viscosity implies increasing cooling of the heat load. And above heat flux value of 2 kilowatt per meter square, the effect of viscosity dominates, which means that ferrofluids with lower viscosity exhibit superior performance. We have also investigated effect of magnetic properties by using ferrofluid sets F4, F6, and F7, and we compare it with the set F0, which is having highest magnetic properties. So for F0, magnetization is around 22 millitesla, F4 is 11 millitesla, F6 is 4.4 millitesla, and F7 is 1.1 millitesla. Evidently, the fluid F7 exhibit lower performance compared to the fluid F0. But Interesting thing happens at the heat flux values of 7 kilowatt per meter square. Even at this lower magnetization value, it starts to exhibit similar performance to that of fluid F0, which is having value 20, approximately um, 95% higher compared to this fluid F7. And all other fluids also exhibit similar performance continuously for all heat flux values. Hence, high heat flux and low magnetization, we can obtain decent performance. And this is important if, let's say, we have a situation where we want lower content of the magnetic nanoparticles, then we can utilize such sets. We have also investigated effect of surface tension, and we did not find any significant change in the performance at higher uh, surface tension values. To understand effect of investigated parameters simultaneously, we have plotted a 3D graph and a heat map. In 3D graph, we compared performance to that of F0. If these values are positive, which means we are getting that much higher cooling compared to fluid F0. F0 is having higher viscosity and higher magnetization to all of these fluids. Evidently, the green curve, which corresponds to fluid F5, provides best performance, and the fluid F4 is the second best. We have also plotted the heat map where we are plotting this parameter magnetization per unit viscosity, since cooling is proportional to magnetization and inversely proportional to viscosity. And we found that when this value is higher than zero point 0.7, we are getting best performance uh, from the investigated fluid. We used fluid F5 for solar cell cooling. We integrated our device with solar cell, where solar cell was placed in the heat load region, and we heated it artificially to investigate its performance as a function of temperature. With increasing temperature, the performance of the solar cell decreases, which is shown by this yellow with this gray band, where no magnetofluidic cooling was used. And whenever we used magnetofluidic cooling, we observed increase in solar cell performance, and we obtained 5% increase for the temperature range of 65 degrees C. Hence, in summary, we can say we have developed a self-pumping, self-regulating magnetofluidic cooling device. We investigated device performance for zero point 0.5 to 10 kilowatt meter square heat flux values and temperature range of 50 to 300 degrees C. And we determined dimensional less numbers and their dominating factors, and magnetization per unit viscosity values above zero point 0.7 exhibited best performance. And we demonstrated application of our device for solar cell cooling with 5% performance improvement. And this device can be used for other applications as well in a broad temperature range. Thank you.